This video is a portion of the general video that gives a full overview of vectors in space. If you want to watch that video, a link is posted in the description. Okay, the last thing we want to talk about is the cross product. This is the second form of vector multiplication. So what if we want to take V1 cross V2? So not V1 dot V2, V1 cross V2. This is equal to the magnitude of V1 times the magnitude of V2 times the sine of the angle between the two vectors. Okay, this is a scalar, right? Times the unit vector normal to the plane that contains V1 and V2. Okay, and then just once again to point this out, I could have put a dot here, or I could have put a multiplication symbol here, or I just leave it as it is, because what is this? This is a scalar times a vector. You look on both sides of this, you've got a scalar and a vector. So a scalar times a vector gives a vector. So that's why the cross product is also known as the vector product. The dot product was called the scalar product because it results in a scalar. This is called the vector product because it results in a vector. This is kind of similar to the dot product. We have this magnitude of V1 and V2 times sine instead of cosine of the angle between the vectors. But it's also very different. This results in a vector. Also, if you do V2 cross V1, it's not equal to V1 cross V2. It's close. It's equal, but it's opposite in direction. So V1 cross V2 is the same vector, but times minus 1. So it's the opposite direction. Because if you think about these two vectors are in a plane here, there's a plane that contains these two vectors, and there's two normals. There's a normal that comes this way, and there's a normal that goes kind of into the page, underneath the plane. There's a normal that comes above the plane. So there's two normals. So we're going to need to know how to choose which normal, right? We're going to take V1, the magnitude of V1 times the magnitude of V2 times the sine of the angle. And then just like the dot product, theta is going to be between 0 and 180 degrees, or 0 and pi. But if you think about for when it comes to sine is only negative for greater than 180 degrees, between 180 degrees and 360 degrees. So if we're restricting theta between 0 and 180, sine is always positive. Sine of theta is always positive. So we're going to have the magnitude of V1 times the magnitude of V2 times sine of theta. This is always positive. We're going to have to choose which normal vector, the one in this direction or the one in that direction. Which one do we use? Okay, to illustrate the main application of the cross product, it's hard to do with just two general vectors like this, V1 and V2. So I'm going to show you how to calculate the cross product first with V1 and V2. So we're just going to learn in general how to mathematically calculate the cross product. Then after that, I'll show you the main application. All right, so you bring the tails of the two vectors together. And in this regard, it's very similar to the dot product. If you pause the video and think about it for a second, calculating this value is just like what we did for the dot product. So we're doing V1 cross V2. So draw a line perpendicular to the line of action of V2. This is theta. And so we're saying V1 sine of theta. So now we're going to get the length of this line, not this length, but this length, times the magnitude of V2. And that's going to be this constant value here. Now, if you think about it, if we're saying V2 cross V1, right? So that we just did V1 cross V2. If we're doing V2 cross V1, well, it's the exact same thing. That's what we saw for the dot product. We get the same value no matter what the order is. So I'm not going to draw it, but what we would do is draw a line that's perpendicular to V1 to the head of V2. Then you get V2 sine of theta, the length of that line, times V1. It's the same thing. So why isn't V2 cross V1 equal to V1 cross V2 like the dot product? Like I mentioned, it just comes from one is going to be in You're going to have V1 cross V2 is going to be in one direction, one normal direction to the plane. V2 cross V1 is going to be in the other direction, the other normal. So V1 cross V2 is going to be equal to -1 times V2 cross V1. Same magnitude, just different directions. One above the plane, one below the plane, however you want to look at it. Okay, but all I've talked about is how to calculate this constant here. This is always going to be a positive constant. Before we talk about this unit vector, let me say one more thing about this constant here. This constant, if you make a parallelogram, so this line is parallel to this vector, and then this line is parallel to this vector, the area of this parallelogram, that's what this constant is equal to. Okay, that's just something to note. And actually, this is a good way to see the plane that contains V2 and V1. Okay, you see the kind of the components of V2 and V1. This V2 is coming out of the page and it's going to the left and up. This is going into the page to the right and up. So it's kind of this tilted plane here. And so the result of V1 cross V2 is going to be a vector that has length equal to the area of this plane, which is this here. And the vector is going to be directed either in the direction of a vector that's normal to this plane, kind of up here, or below the plane, perpendicular but below the plane, one of those two directions. So we need to do two things here. We need to determine which direction is it going to be, and then we need to determine the components of this unit vector, right? How are we going to determine the components of this unit vector? So first, which direction is it going to be? This is where the right-hand rule comes into play. So what you do is you take your right hand, put the palm of the right hand along V1 with the fingers, the curl of the fingers facing V2, push V1 to V2, and your thumb is in the direction of the normal vector. Now, if it was V2 cross V1, you would put the palm of your right hand along V2 with the curl of the fingers facing V1, push V2 to V1, and the thumb is facing in the direction of the normal vector. So we're doing V1 cross V2. This is going to be our direction. This is going to be our direction. So how do we determine the components of a unit vector in that direction? One way to do it is you take the determinant of a 3x3 matrix. So in the first row, you put I hat, J hat, K hat. The second row, you put V1X, V1Y, V1Z. Third row, and so taking the determinant of a 3x3 matrix, you get and then just make sure you get your signs right. If the component of V2 in the Z direction is in the negative direction, you need to put a negative here. If you just do this, it will work out whether the normal vector is above or below the plane. All of that is built in. If you did this for V1 cross V2, you would get a vector. If you did this again for V2 cross V1, you would get another vector. And you would find that that vector is just -1 times the first vector you calculated. Now, you can do it this way, but I'm going to show you how I like to do it. That doesn't involve the determinant. So let's say V1. All right. Now V2. Okay, let's say this was V1 and V2. How do we calculate the cross product? Let's calculate V1 cross V2. Well, what you do is you just write out the vectors in component form like this and put the cross. So say okay, now what we're going to do is we're going to distribute all of this. So first we're going to say, what is 8 I hat cross minus 4 I hat? If you're crossing two unit vectors that are the same, that's going to be 0. So if you have j hat cross j hat, k hat cross k hat, I hat cross I hat, that's always 0. So 8 I hat cross minus 4 I hat is going to be 0. Why is that? Because the sine of the angle between them is 0. Sine of 0 is 0. All right. So now, next. So we just did 8 I hat cross minus 4 I hat. What is 8 I hat cross 6 j hat? So positive 8 I hat cross positive 6 j hat. That's going to be, so this is what you do. Put 8 times 6. Now, if one of these was negative, you would just put it as a positive. So you're just going to put the magnitudes here. Now, what we need to do is cross positive I hat with positive j hat to get to the direction. Okay, so for this coordinate system, positive I hat cross positive j hat is positive k hat. So this is positive k hat. Okay, next, 8 I hat cross 2 k hat. Just put 8 into, if one of these was negative, just put it as positive. And then cross positive I hat with positive k hat. If let's say this was minus 2 k hat, you would put 8 times 2, positive 8 times positive 2, and you would cross positive I hat with negative k hat. But here we're doing positive I hat with positive k hat. All right. So let's see. Put the palm of your hand along the x direction with the fingers facing the k direction, the curl of your fingers facing the k direction. Push x onto k. And where is your thumb facing? Down. Minus j hat. So this is minus j hat. Okay. Now we've got 5 j hat cross minus 4 I hat. So put 5, put positive 4. Now we want to cross positive j hat with minus I hat. So put palm of your hand, your right hand, along j hat, along the y, but the fingers facing minus I hat. And now push the y-axis onto the minus x-axis. And the thumb is facing out of the page in the positive k hat direction. All right. Plus 5 j hat cross 6 j hat. J hat cross j hat is 0. 5 j hat cross 2 k hat. So put 5, put 2. Now let's cross positive j hat with positive k hat. So positive y direction with the curl of the fingers facing positive z direction. Push positive y to positive z, and where's the thumb facing? In the positive x. So in the positive I hat direction. Okay, minus 3 k hat cross minus 4 I hat. Just put 3, positive 4. Now let's cross minus k hat with minus I hat. So in the right hand, the palm in the minus z direction, and the fingers facing negative x. Push negative z to negative x. The thumb is facing in positive y. Okay. Minus 3 k hat cross 6 j hat. So just put a 3, put a 6. Now cross minus k hat with positive j hat. Minus k hat, positive j hat, positive I hat. Okay. Minus 3 k hat cross 2 k hat. K hat cross k hat is 0. Okay, so now let's write all this out. We've got 48 k hat minus 16 j hat plus 20 k hat plus 10 I hat plus 12 j hat plus 18 I hat. All right, so let's put the I hats first. We've got 10 plus 18, so 28 I hat. Okay, now the j hats, minus 16 plus 12, so minus 4j hat. And then 48 plus 20 is 68k hat. And there you go. That's V1 cross V2 for this case. The parallelogram made between V1 and V2, the area of that's the magnitude of this vector. If you took 28 squared plus 4 squared plus 68 squared square root, that's the magnitude. And the direction of this, you have to draw these vectors and then push V1 to V2. And so you'd see whether that's kind of above or below the plane that contains the vectors. And this direction is going to be normal to that plane. If we did V2 cross V1, V2 cross V1 would be minus 1 times this. So minus 28I hat plus 4J hat minus 68K hat. So that's how I like to do it. I like writing out the vector components and crossing it like this and doing like, if you feel like you're doing a real multiplication, and then you don't have to memorize the determinant and watch all of those signs. So I like doing it this way, but if you want to use the determinant, that's fine. Okay, so the only thing that's left to talk about is, what is the cross product? What is the point of the cross product? We saw the application of the dot product. What does the cross product mean? Well, what I think is probably the main reason why the cross product was invented was for rotations. So like in engineering mechanics, you have forces. Sometimes you want to be able to calculate the tendency of a force to cause a rotation about something. If you have a wrench, if you're applying a force to a wrench, well, you have that force, but also how far is that force from the rotation point is something you want to calculate, because it's stronger. The bigger the torque, the larger the torque, the more force turning force is on the bolt. Those forces might cause that body to spin, though, like throwing a baseball. You have that forward linear motion, but also there's like a spinning motion, and that's why you have this as a vector, the cross product as a vector, because you could have a force that's causing a rotation. You want to calculate the magnitude of that tendency of rotation that's being caused. So the more force you apply, and the farther the distance away from some point, right, the larger the wrench, the more tendency for rotation you're causing. That full tendency is the magnitude of that vector. But then you also have the direction of that vector, which is that direction of that vector represents the axis of rotation. So let me show you what I mean. So we still have V1 here. Let's imagine that V1 is a force. We can imagine that it's a force. Now here's a point. We want to determine, if V1 is a force, we want to determine the tendency of this force to cause rotation about this point. How do we do that? Okay, well, here's the line of action of the force. Now we're going to draw a position vector from the point to anywhere along the line of action of V1, of the force. Let's do it here. This is a position vector R. And what we want to do is say R cross V1. Okay, now why can we arbitrarily choose where this R goes to the line of action? I mean, we could have drawn a position vector all the way out here. Why? Because for a tendency to cause rotation, for the tendency of this force V1 to cause rotation about the point, all we're looking for is the perpendicular distance between the line of action and the point, right? All we're looking for is this. Well, this is V1 here. Okay, what we want is V1 times this distance, this perpendicular distance, right? That's the tendency to cause rotation. Okay, now if we slide this vector, this R vector up here, okay, what do we see? Well, we've got this is the angle theta. This is the angle between R and V. If you put their tails together, this is the angle between R and V. But look, that's this angle. Okay? So if the angle between r and v, theta, is that. What is r sine theta? That's d. R sine theta. That's what we've got. This is V1 times D. So that's okay. So great. We've got V1 times D. But remember our goal here is to calculate the magnitude of the tendency to cause rotation. But there's two different ways. There's two different directions that the rotation can be going. And then furthermore, how do we represent that direction as a vector? That direction of rotation as a vector? Well, what we do is we say that direction is the axis of rotation. Well, okay, what axis is V1 causing rotation about? Well, it's going to be the axis that's normal to the plane that contains R and V1, right? It's going to be like this axis. I know that this is kind of hard to visualize, but imagine this is perpendicular to the plane containing R and V1. So V1 is causing rotation about this axis. And the direction is based on the right-hand rule. So put the tail of R at the tail of V1. So put your right hand along R, push R to V1. It's going to be below the plane, kind of into the page. So in this direction. And so you see if you put your thumb facing this direction, the curl of the fingers is the direction of rotation, right? V1 is causing rotation in this direction along this vector. And so you know the direction of rotation, and then the magnitude of that tendency to cause rotation, the V1 times D, is this. If V1 were pointed in the opposite direction, you'd get the same magnitude, but you'd be rotating in the other direction. So that shows you what the cross product is used for and why it's a vector. Because rotations, tendencies to cause rotations, and actual rotations have both magnitude and direction. Okay, what about properties of the cross product? We already mentioned that V1 cross V2 is minus V2 cross V1. What if we have a constant times V1 cross V2? Okay, this is or okay, now what about this is equal to okay? Now just remember, when you're looking at these, the order matters. You can't change this to V2 cross V1 unless you put a minus sign. Okay, now comparing this to regular multiplication, here's our first inconsistency. V1 cross V2 is equal to minus V2 cross V1. That's not, that we don't see that with regular multiplication. This is the first difference. Okay, what about this? This is just like regular multiplication. What about this? This is just like regular multiplication. So this is good to know. When you're thinking about how do operations of vectors compare with regular operations for addition, subtraction, and multiplication, we haven't really talked about division, the idea of dividing vectors yet, but so comparing to regular addition, subtraction, and multiplication, all vector operations are consistent with the operations on normal numbers except for the commutative property with the cross product.